Yeah, thanks a lot. So this is the second part of my series of 2 talks on kind of stacks of equivariant vector bundles and categorical p-adic Langlands. So I cheated a bit by putting a recap on yesterday's talk on the boards. So I want to recall that I'm aiming for, in a rough formulation, a functor from a derived category of local analytic representations of the group, let's say I specialize to GLN, of the group GLN QP to the stack of coherent sheaves on the stack of equivariant vector bundles on the Fargues-Fontaine curve in a rough formulation, ignoring many subtle or not so subtle issues. Yesterday we talked quite a bit about the definition of the stack of equivariant vector bundles on the Fargues-Fontaine curve and this other 2 stacks to which it maps, the stack of beta-1 plus representation, respectively the stack of C representation or CP representation that via characteristic polynomial of the Sen operator maps to some affine space that hence one can consider or, well, deserves the name space of Hodge-Tate rates. And I've wrote down some results about the geometry of these spaces, in particular including that this stack here, étale locally on this affine base, looks like the stack quotient of the Lie algebra of GLN by its adjoint action. Okay, and I ended with writing down a certain action of some monoidal category of sheaves on a Hecke stack on sheaves on LS GLN Fargues-Fontaine, which I want to recall now in the middle. That I had defined something like Hecke GLN beta-1 plus, Hecke stack for beta-1 plus representations. So basically you should think of this being the fiber product of 2 copies of the stack of beta-1 plus representations over the stack of beta-1 representations, so where T is inverted. Let me put this into quotation marks because I didn't at all define something like this, but kind of with, I hope, the more or less obvious definition of what that should be. This, what I've wrote yesterday, identifies with a fiber product like this. Okay, and I had argued that the bounded derived category of coherent sheaves is a monoidal category. And it acts on sheaves on the Fargues-Fontaine curve. So I hesitated and dropped bounded up here because it's certainly expected that it preserves boundedness, but so far I can't really prove it. Has to do with whether or not one can show that this map down here has bounded Tor dimensions or not. Okay, but here I definitely want to have some boundedness condition to have something well defined. And so I maybe should have made this example before saying this the sentence. So that's an example what the stack looks like. So just as a reminder for the kind of explicit computation and geometric descriptions from yesterday. So if I have lambda 1 up to lambda n integers that are pairwise distinct, and I give myself a second set of pairwise distinct integers, then I can view them as the zero of a certain polynomial, which give me kind of 2 points, x and y, in my space of Hodge state weights. And then I can describe what the completion of this Hecke stack completed at these pair of points x, y is, in a similar fashion as I did yesterday for the stack ls gln b1 plus. Okay, and so we saw yesterday that if I just do one of these factors, then you see some completion of some Grothendieck-Springer resolution. Okay, and now this kind of Grothendieck-Springer resolution should appear twice. And hence, what you will see here is something like gln tilde times gln tilde, the prior product over gln itself, divided by gln, and you complete above the nilpotent locus. Okay, so you see the completion of some Steinberg variety. Okay, that's just an example about the geometry of this Hecke stack. And the first question I want to address today is the question, is this monoidal action interesting from the point of view of p-adic local Langlands? From the point of view of p-adic Langlands. Okay, and obviously the answer is yes. Yeah.
Quickly recall what means Moduli action of the category.
Maybe not. Well, I mean, like, in some sense, for your intuition, just drop the derived thing and just have a monoidal category that acts on an abelian category. Okay, that's. I think I don't want to go into technicalities for this talk, and maybe ask me afterwards. That's fine. Okay, so of course the answer should be yes, otherwise I wouldn't have done it. And hence I want to talk a little bit about what's called Harris-Chandra bimodules. Okay, so let's start right away with the definition. A Harris-Chandra bimodule M for a reductive group G. Well, let's say my group is over QP. The base field doesn't matter. Maybe you want to be characteristic 0, but like for this very algebraic definition, it just doesn't matter at all that we are over QP. Is a U of G tensor U of G op module, finite degenerated maybe, such that M restricted to one copy of U of G. And I have to tell you along which map I want to restrict. So there's a diagonal map from U of G to U of G plus G op. And I just, on the level of the algebras, take X to X comma its transpose. Such that if you restrict to this diagonal, this just isomorphic to the direct sum of algebraic G representation. Okay, so this direct sum certainly in general is allowed to be infinite, but it's a infinite direct sum of finite dimensional representation. Okay, so that's what an Harris-Chandra bimodule is. And I want to note that Harris-Chandra bimodules give you a monodal category. That I want to denote just by HCG. Okay, monodal, you just tensorize over the Lie algebra, over one copy of U of G, passing between left and right modules using U of G op. Okay, and if you take two such things and you tensorize over one factor of UG, then there are still two ones remaining that still can act. And so that's kind of by design, you get a tensor product which gives us a structure of a monoidal category. Okay, so here are some examples. Of objects in this category. So V, an algebraic representation of G. Then you can attach a Harris-Chandra bimodule to this by inducing along this diagonal map. Let's call this module M of V. These are Harris-Chandra bimodules. And in fact, you could say these are all the Harris-Chandra bimodules I'm interested in, because these give you projective generators of this category. Okay, so you already know quite a lot about this category because you know a very nice set of generators. Okay. So one other thing is that Harris-Chandra bimodules, so HGC acts just via the tensor product. For example, on the BGG category O. Or it's, say, deformation which I'm going to call O tilde, where there's some theory that you have this block decomposition of the category O, and then there's the notion of deformation of the blocks and so on, that if you don't know, at least for my talk, I guess you can roughly ignore, and just want to give you a few examples and a flavor for this category that you're maybe not so familiar with that category that maybe at least some of you are more familiar with. Okay, and if you start with some lambda dominant algebraic character, which giving rise to chi lambda infinitesimal character. So that's the center of Z and U of G, the center. Okay, so then what you could do, you can take Harris-Chandra bimodules for G and complete, well, I mean, like, this is now a category which is linear over two copies of the center. Okay, so you can complete this with respect to a pair of infinitesimal characters. Okay, and in this case, this just becomes the same thing as, well, the block of the category O with kind of this infinitesimal character, respectively, its deformation. So don't think too much about this deformation. I just want to tell you, you can produce examples of Harris-Chandra bimodules that look like objects in the category O. Okay, so there's something you can do. And how is this done? By acting on M of lambda, the dominant Wermer. Okay, respectively, its deformation. Okay, and the reason that I'm making the statement about kind of deformations of category O and blocks and so on is just to kind of get an easy way to state these things and not to worry too much about kind of the precise action of the center on the individual blocks of the category O. Like then kind of the statement would be harder to write down. Basically, the claim is that using very classical Lie algebra representation theory, you can cook up some very nice examples of Harris-Chandra bimodules. All right, and here is the reason why I care. The proposition, the category of Harris-Chandra bimodules acts on the category of local analytic representations. Okay, and I just want to convince you why this is the case. So let's quickly sketch this. So let pi be a local analytic representation. Then I want to argue that pi in a canonical way is a module over the Lie algebra. Okay, so that's something fairly familiar in local analytic representation theory. So let me just indicate, for example, why. Then pi canonically is a module over the distribution algebra of G QP. So that's the locally analytic distribution algebra. Which just contains the enveloping algebra of the Lie algebra. Another way to put this is that local analytic by design means that you can just, by the standard formula, derive the action of the group and get the action of the Lie algebra. Okay, so you have Lie algebra action, and for V in algebraic representation, of G, well, you can just compute, or you can just guess what the action of this Harris-Chandra bimodule attached to V on pi is supposed to be. If you just compute what this tensor product is, keeping in mind that this guy here was induced, then it just turns out it's just the same thing as V tensor pi over the base field, which of course had the diagonal action of G. G of QP, I should say. Which still is locally analytic because I just tensorized with something finite dimensional algebraic. And this is an isomorphism as UG representations. So the left-hand side here, a priori only, is a UG module. So you see what the G of QP representation on that is supposed to be. And then you want to use that these M of V are projective generators and just check some compatibilities to upgrade this action. Okay, that's maybe the quickest way to indicate why you should expect to have this action and how this is supposed to look like. And
Can you write down an interesting thing which is not acting by V but by something else?
well, something like a Werner module in some sense, but I mean, you get interesting things. Well, I mean, like these things are interesting, but you get other interesting things if you see that you in some sense just can write down a complex of Harris-Chandra bimodules with kind of maps between them that you only have after induction, that do not come from maps between algebraic representations. Right? And this way you can cook up a lot of interesting examples. Though I maybe don't want to write down a particular example of this on the board. No, not like that. Let's see whether I'll be able to say something about all extra representations. So we have one monoidal category which acts on local integral representations, and I introduced another monoidal category which is supposed to act on these. So I should talk about a bridge between these monoidal categories. That's the following theorem on joint work in progress with Roman Bezrukavnikov. Okay, and well, let me just give the formulation for GLN because I only introduced these Hecke stacks and so on for GLN. But I still want to index things by G and by its dual group G check, even though both, of course, are GLNs. Okay, and the result is there exists a fully faithful embedding of monoidal categories of Harris-Chandra bimodules into I don't need to write it on the derived level. That's true on the abelian level. Let me work on the derived level because a priori with my definitions from last time, the monoidal structure here only makes sense in the derived world. You will see that it's a consequence of the theorem and the construction that on the essential image of this category, the convolution structure does preserve the heart. Okay, so that this actually is a statement about abelian categories, but a priori the monoidal structure here is only defined on the derived level. So hence it's kind of cleaner to say that as a statement about derived categories. Okay. Yep. Thanks. Okay. And once you have this theorem, there's of course the obvious desideratum 1. I'll give some example of this in a second. I just want to map, write down the obvious thing that you want to have. So this functor AGLN, for which I'm aiming up there, is compatible with, you have this D verb LA, G of QP, and you want to map it to D of LS GLN on the Fargues-Fontaine curve. And here you have an action of the Harris-Chandler bimodules. And here you have an action of this Hecke category of sheaves on the Hecke stack. So, question?
No, just I don't understand the notation. Like, what is the symbol or the first symbol?
Oh, like it's just a name that I gave to this function. Yes, but of course I was allowed to write something before starting the talk, as you stole 5 minutes from me. No, sorry. Okay, so you have this model action, and whatever you want to have should be compatible with this. Okay, so let me give you some feeling for what the field looks like. Okay, so examples. So let's do the case of GL2. Okay, so the Hecke stack for G check with beta 1 plus coefficients has a closed substack which is kind of the bounded by mu part. For mu in X lower star of the dual torus dominant co-character. Okay, so that's kind of closed sub where the modification is bounded by mu. Okay, so which just comes from the user certification on affine Gauss-Mannions that you know. But now you notice that this here, of course, is X upper star of T dominant. So, well, you're not on the dual side. And so the functor has the property that if you take this algebraic representation, the irreducible algebraic representation of highest weight mu, and induce it to get Harris-Chandler bimodule, then you know where you want to map it. Namely, you want to map it to the structure sheaf of this bounded by mu part. Okay, and in some sense, the idea is that something like this should always happen in full generality, that you want to look at the structure sheaf of the bounded by mu part. It just doesn't work, and only works for GL2, because GL2 has the property that for the irreducible algebraic representations, all weight spaces are one-dimensional. Okay, and that's not true for groups other than GL2 or maybe SL2. You have multiplicities in the weight spaces, which imply that this sheaf that you can see here can't be locally free. Okay, and then you have to think a bit and modify a bit and work a bit, but yeah. Yes? Of course, yes. There's also a map between these Harris-Chandler bimodules. There's none between the algebraic representations, but between the Harris-Chandler bimodules, of course, there is. Oh. Vitas is asking again whether I can give some examples which are not in use. What was it? Yes, there was an example to come. So On purpose, I recalled before that this thing looks like the Steinberg variety after completion. Okay, so that's my second example, which does work for GLN. So let's say lambda in X upper star plus dominant co-character, and then you have chi lambda, and then I told you that if you complete at two pairs of infinitesimal characters, then this becomes isomorphic to a block in the category O. Okay, something like this. Okay, and in particular, in here, you have the Werner modules. Okay. Okay. On the other hand, I told you that the stack of this Hecke stack if you complete this, well, now because of the normalization of the Harris-Chandra isomorphism for the center, you have to shift this. So you have to take maybe lambda plus half sum of the positive roots, comma lambda plus half sum of the positive roots. So that's where you want to look. But we saw that this is the completion of the Steinberg. With 0, 0. Okay, and sorry? Oh yes, mod GLN. Mod G check completed at 0, 0. And this now has a map to two copies of the flag variety. So G check mod B check times G check mod B check, and then mod G check. And this has its Bruyère stratification. So you have in here the UW a Bruyère cell. Okay. And what you can do is you can take, well, I mean, what I maybe would call XW mod G check in here, and then complete it at 0, 0. Yeah. Now this is an isomorphism of formal stacks. Okay, and here the XW in the Steinberg is the closure of the pre-image of your Bruyère cell, and it turns out that these make up the irreducible components of the Steinberg. Okay, so that's how you describe the global geometry of the Steinberg variety. It has these irreducible components, and you can, in some sense as well, complete just one of these components. Okay, and then this Werner module has the nice property that it just maps to the structure sheaf of this guy. Completed over 0, 0, up to two annoying issues. The one is that you have to deform, and the other thing is that you have to take the dual Werner module. Okay, so that's kind of the second kind of example that I can offer what this functor does. And in some sense, the restriction of this functor that I would use over there to these completions, this was present in work of Bezrukavnikov already before, and which can be read off from his equivalence in this two geometric realization paper.
So you said
Yeah.
you can realize all the Arishton modules as sheaves on the triangle?
No. It's a fully faithful embedding. It's not essentially surjective. It's far from being essentially surjective.
I know, but like in Bezrukavnikov's equivalence, can you map all Arishton module in equivalent sheet? Can you see all Arishton module as a subcategory of?
I mean, that's the claim, right? That I can map all Harris-Chandler modules into coherent sheaves.
Yeah, but at the level of the Steinberg. In Bezrukavnikov equivalence.
Yes?
But it's kind
Yes.
of globalization. Because when you see
Right. I mean, like the thing up there was a globalization of a functor that you cook up here. So what Bezrukavnikov's equivalence up here gives you is only something on these completions. And this statement up there can be interpreted as you kind of maybe interpolate these. Right. Okay.
maybe you just like this, but so this completion doesn't seem to lie in the category that you consider.
What?
So, I mean, you want something with ACG, and now why does completion somewhere here? And so how is completion related to the?
I mean, completion always means restrict to things. Where on the left-hand side, completion just means restrict to the full subcategory of HCG, where the action of the center factors through some power of the kernel of this character. And what? Well, it's a deformation of a block.
The drafting one is kind of stronger than what happens in the second. Correct?
Well, I mean, the derivatum 1 is strong in the sense that it talks about a conjectural compatibility in a conjecture. Right? So I mean, like the
second point means you restrict this to some Artinian things or something like this, and then you get this.
Right. Okay. So these are hopefully some concrete examples of things with which you can act on the left-hand side and with which you can act on the right-hand side, and where you maybe would like to know that this is compatible. So there was this one remark due, of course, that in the work with Roman, we maybe certainly don't consider B1 plus representations, but we do this for this untwisted version using formal logarithmic derivations that I wrote down last time. And this in some sense. So strictly speaking, this is just kind of a twist of the result that we're proving. The second thing is that's a fully faithful embedding. And you might wonder whether there are more interesting actions of things in here. And well, I mean, like, of course there are more sheaves in here, but I want to caution you that there is something which is not in there, even though you might expect this. So that kind of caution. There is no action of the representation of the dual group, so which would be derived category of the coherent sheaves on point Moduli check on Deo LS GLN Fargues-Fontaine. Okay, why this? as there is no map of LS GLN beta 1 plus. So you might say you want to realize this using this Hecke action, but you don't have a map from this stack to point mod GLN. Okay, so here it looks like you want to have a canonical map down to GLN, okay, because here you have, but this you only have etal locally, okay, and the fact that this only etal locally is the case, but not globally, well, gives you, in fact, well, you have to check it, but it gives you that there's no map of this to point mod GLN, and hence you have no direct action of web gcheck. But there was a way out, but for v check in web gcheck, we can instead consider the functor from, we take some f. This lies in the B coherent LS and gcheck Fargues-Fontaine. And what you want to do is you just want to tensorize with vcheck, but doesn't make sense. But what makes sense is to push forward the universal gcheck bundle over the Fargues-Fontaine curve along this algebraic representation. Yep.
On the other hand, you have an action of rep G by evaluating this using the this M of T. You can go from D to M of T.
Yes?
And then act as a horizontal.
Right, but this I already described. I mean, I already described that there is an action of web G, which is kind of something new and unexpected in the framework of categorical Langlands. The thing that you usually have is an action of representations of the dual group, which definitely shouldn't preserve this category, but it acts here and it, in some sense, does something interesting on this category for which you have to kind of go out of the world of just representations of GL on N of QP. But it takes the shape that it moves you out of this category of coherent sheaves, right? It moves you to a coherent sheaf tensor, some kind of vector bundle on the Fargues-Fontaine curve. So this here rather is in LS gcheck Fargues-Fontaine times the Fargues-Fontaine curve. Okay, and this this can't be seen on the level of this Hecke action, at least not without kind of getting rid of this etal local isomorphism. But maybe that's just a side remark. Okay, so that's one desideratum. Okay, and maybe first erase. I want to have some more desiderata for the functor. I want to talk about parabolic induction. So we call that if we have T in B in G, then we have parabolic induction, locally analytic one, from local analytic representations of T to locally analytic representations of G. Okay, and I want to prescribe what the corresponding effect on the Galois side is supposed to be. So we, strictly speaking, because I haven't introduced these objects beyond the case of GLN, G is still GLN. Okay, so on the Galois side, I can do the same construction as I did for the Borel in the dual group and for the Torus in the dual group. So that's a stack of equivariant vector bundles E rank n plus fill E complete or full Galois stable flat. Okay. That's what the thing is. That naturally pops out if you want to define what the stack is for the Borel. And then very similarly, you can define something for the Torus, which just looks like the stack for GL1 to the n. Okay, so this one certainly also is quite familiar. GL1, GM. Right, but I mean, you're right, the index 1 is so hard to read that GM is maybe the better thing. Okay, so on the Galois side, you now run into some, well, maybe consider it first just a technical problem, which is familiar from the theory of vector bundles on algebraic curves, where you form some bun G and some bun B and so on, namely that a map like this has no chance to be proper. Okay, so beta is not proper. Okay, and so alpha is not proper, no, but alpha you also don't want to be proper. The idea is that you want to pull back by alpha and push forward by beta. Okay, so you want beta to have properties such that push forward is nice, and you want alpha to have properties that pull back is nice, like bounded Tor dimension or something like this. And the latter is the case for alpha. Well, should be and is true up to GL4, and it depends on how much I actually can prove about these. Okay, so the way out is we define some Greenfeld compactification, or construct a Greenfeld compactification. LS we check Fargues-Fontaine compactified with the map beta compactified to LS G check Fargues-Fontaine and here to LS T check Fargues-Fontaine. Okay, and well, I guess for the sake of time, I will not say too much for what this Greenfeld compactification is, but the idea is we allow that the filtration to be non-saturated over B to 1 plus. Okay, so that the subquotients are not necessarily supposed to be vector bundles or line bundles. What? Yes. Yes. More general filtration. So there should be filtrations after inverting T, and over B to 1 plus, I have to be careful what precisely for conditions I have. But like I could kind of give the local description for the corresponding compactification of the stack of B to 1 plus representations, but well, which again would involve some things with Steinberg varieties and so on. You can make this completely explicit, but I guess I tortured you already enough with this local completions, and hence I want to leave it like this. Okay, and then here is a desideratum number 2. Yeah. There's, well, by the precise definition of what this actually is, there is no problem of extending alpha to this. And it's kind of, like, the answer to your question is kind of moved into the construction of what this object actually is. So there's a desideratum 2 that I have. So I have this D verb LA of T, which I can map via some functor for conjectural functor for the torus to D of the stack of T check bundles on the Fargues-Fontaine curve. And here I can induce well, I maybe make some normalization, which has to do with modulus characters and so on. So it's kind of some normalization of my parabolic induction that I don't want to dive into too much. And here should be some functor for G, which is going here. Okay, and then here I want to do some pull-push construction. Namely, it's supposed to be alpha upper star, beta lower Schwieg. Beta bar lower Schwieg, sorry. And here I also have to put a normalization tensor, let me call this rho prime. So these are normalizations. Where delta B is something like the modulus character. Well, plus something algebraic as well. It's not just a smooth character. And the rho prime is the algebraic character. Well, which one do I have in my normalization? 0, -1 up to -n plus 1 in X upper star T check. Okay, and so note that this stack here has a map to T check because I described yesterday what the space looks like for the torus. So I can twist here with algebraic characters. And it's just a side remark for those who are a bit familiar with the theory. So if you formulate this for a general group, you might, you better want to formulate or define the stacks not using the dual group, but the C group. Okay, and those who know the C group in some sense will more or less automatically write down the correct definitions. And the C group takes care of a lot of annoying twists. Okay, so in particular, the C group would just take care of this twist, this normalization twist here, this would just disappear. The annoying thing is the C group can't take care of this normalization twist down here. Okay, so because this is kind of the central shift of the half sum of the positive roots of the dual group, not of the group itself. So if you would like to get rid of this, you would have to pass to the C group on the automorphic side. Okay, which you maybe don't want to do because then you can't talk about representations of groups such as SL2 anymore. Okay, so instead, the way out should be or has to be that here you don't talk about coherent sheaves anymore, but you have to talk about twisted coherent sheaves for a certain U2 gerb that you more or less canonically want to define. Okay, but that's kind of a side remark about normalizations and which kind of normalizations are kind of can be discussed away and which ones can't be discussed away. Yeah. Okay, whether I can say something about the problem that beta bar is not proper. Well, I mean, the easy answer, at least for you, maybe is that if you want to compute kind of what the thing does or candidates for this in spaces of p-adic automorphic forms, you just don't get the correct answer without compactifying. So in particular, all these companion constituents about which you made a conjecture, you should see appearing, and you don't see appear these if you don't compactify. All right, so it's like it's true. I was kind of cheating a little bit when I said the main problem is it's a technical problem is it's not proper and then just compactify. There are kind of better reasons than just saying it's a technical problem. Yeah. I want to mention something in the end where I might give a better answer to this. Yeah.
I have a question about the normalization. When you say you work with C group,
yes.
Doesn't it mean like you just change the Galois set, but you keep the working set the same?
Yes.
So why does it take care of this delta p bar? Because the complete side isn't the same.
Well, but I mean, in some sense, if you want, you can move this normalization down here as well, right? If you just kind of change something. And that's exactly what pops out if you write things with a C group.
Okay.
Let's forget about this. It's true, beta bar is still not proper. And this indeed causes some problems, but I wanted to ignore these. Well, in the preceding talk, Pierre said at some point, it's better to lie a bit. And so I think I want to do something similar here. Okay, and then there's, of course, the derivative number 3. Is that you know what the map for the torus is, or the functor for the torus is supposed to be. Okay, that for the torus, you know everything by local class field theory. I don't want to make this precise, but roughly this uses the explicit description of the stack for GM in terms of the modular space of characters that I gave yesterday. Okay, so using the description of LSGM in terms of moduli of characters of QP star. This is very nicely worked out and explained in the second paper of Rodriguez Camargo and Rodriguez Raquinto on solid analytic representations. And I should warn you, unlike most instances of categorical correspondences that you see, in this context, already in the abelian case, this is intrinsically derived. Okay, there's no way of stating this as a fully faithful embedding on the abelian level. Okay, these are three things. And I want to tell you that there's a consequence of 1, 2, and 3. Okay, so namely, let pi be a smooth representation. That happens to be principal series, or in the principal series block. That's important. Okay, then its image under this functor. Well, smooth representations are certainly locally analytic, so I can apply this conjectural functor to this. This is determined by 1, 2, and 3. Okay, so I want to tell you that once you know what parabolic induction should do, and you have this action of Harris-Chandra bimodules, you know what happens for quite a lot of smooth representations. Even locally algebraic. Right. But locally, to get from smooth to locally algebraic is in some sense easy because it's tensorizing with an algebraic representation, and that is exactly kind of taken care of by the action of some Harris-Chandra bimodules, namely the easiest possible one. Okay, so in some sense, smooth is the base case for this. Why that? So you want to use so that you know what happens. Like you basically want to know what happens on induced representations, on smooth induction itself. Okay, so want to compute a G of a smooth induction so delta a smooth character, or maybe I induced from the opposite, but well, because that's what appeared in my compatibility. I want to compute this as AG of the local analytic induction. Tensor, and then I want to put here a complex of Harris-Chandra bimodules. Okay, and basically what the thing should do is it should mimic the BGG resolution of the standard representation. Okay, so this kind of corresponds to BGG resolution of the trivial representation. Well, I guess maybe in case I'm using this induction instead of some All-Strauss things, I should say dual BGG resolution, but let me not kind of care about science for this. Okay, so it's in some sense clear by a formal argument that it's determined. It's maybe harder to compute what it is. I guess so far I can only compute this either generically or for GL2 and GL3. But still, there was a clear expectation of what the outcome of that computation is supposed to be. And this expectation you then can formulate for all blocks, not just the principal series blocks. Okay, so it's kind of an expectation backslash desideratum. Number 4. Sorry? Well, the Harris-Chandra action takes place in like this Bernstein blocks, you mean, or? I mean, this takes place in an entirely different world, right? I mean, like once you're here, there's no way of talking about any kind of Bernstein blocks. Maybe I don't understand the question. I think I just don't understand the question. Maybe we can discuss afterwards. Okay, and so here's the final expectation or desideratum that I want to talk about. Okay, so we take LS and you check Fargues-Fontaine. So this contains a certain closed sub, LS G-check Fargues-Fontaine DRAM with Hodge-Tate weights 0, 1 up to n-1. So that's a closed substack of objects that are DRAM or vector bundles that are DRAM of, well, the Hodge-Tate weight I wrote. Okay, and it turns out that this here is isomorphic, at least over QP anomified, where you can undo some twist to the product of the flag variety parameterizing the Hodge filtration on D1. Sorry, maybe like this. So there's a flag variety occurring, and that's the stack of n-dimensional Bell-Dean representations. Sorry? No. I take all vector bundles on the Fargues-Fontaine curve, not asking whether the thema stable slope 0 or something like this. And hence I also don't have any admissibility or weak admissibility condition down here. Okay, so that's the space I have. And then and with a simulation. So then for pi, a smooth representation it's a desideratum, so I just write AG of pi is equal to, well, here I have smooth categorical Langlands. Applied to pi. Okay, so this gives me a sheaf on the stack of valid representations. The sheaf on there. And then you get something on the second factor as well. And you get the equivariant line bundle on the flag variety, which is attached to precisely the character that also something like. Okay, that's an equivariant line bundle. On G check mod B check, corresponding to well, this character n minus 1, 1, 0, and x upper star of T check. Yes. So that's kind of what comes out of Fargues-Fontaine or like for GLN. I mean, it's even kind of explicitly written what this is in Benz-Eugen-Hellmann, and so that's, well, at least for GLN, that's something where you kind of know what this functor is supposed to be and supposed to do. Okay. And on principal series blocks, in some sense, it's the expectation that this is nailed down by this compatibility with parabolic induction and the action of the Harris-Chandler modules. And the same with the remark is that similar for locally algebraic representations. About which Christoph already asked. Okay, so this is finishing my program that I wanted to cover yesterday.
The bottom G check, does it somehow keep track of the
Say it again?
I was wondering what kind of information does this line model give?
None. I mean, it's in some sense a twist or normalization or something like this. Well, I mean, like in some sense, I would say if you just restrict to smooth representation or locally algebraic, it doesn't give you an extra information. You can twist by any line bundle and write down a similar functor. Whether or not you can then vary this in families to get away from the locally analytic part is something else. I would claim that if you don't do this, and for example put the trivial line bundle, then you couldn't vary and extrapolate from this, which has a little bit to do with the fact that in this p-adic context, the Whittaker sheaf is not supposed to sit on the principal open stratum, but somewhere else. Well. Yeah.
So start from smooth pi, apply your conjectural AGLN.
Yes.
Restrict it to a closed subset and it gives test. Is that what you mean?
Well, I mean, if you apply AG of pi, then you get a coherent sheaf that is supported on a closed substack and is given by precisely this recipe. Right. Okay. I have roughly 10 or 15 minutes, but I maybe want to or should say something about what I announced yesterday, that I wanted to say something about overconvergent p-adic automorphic forms. Because like the okay. or modular forms, or maybe rather modular symbols. Okay, and so let's first forget about overconvergent p-adic and just talk about modular symbols, or the cohomology of the classical modular curve. So let's fit the compact of an open level, and then you have the corresponding yk modular curve over Q of level k. Okay, and so if lambda in x upper star of t is a dominant co-character, then we have v lambda, an irreducible algebraic representation, and from this I can cook up curly v lambda, the corresponding étale local system. Oh, yes. That was a bit embarrassing. Thanks. Okay, it's an étale local system. And you know that over C, over the complex numbers, how this is done, you just take h times v lambda and then g of the finite adels modulo your level, and you project it down to h times g of af modulo the level, and then you mod out by the diagonal g of cube action. Okay, so that's the usual procedure, how you define and cook up local systems from algebraic representations. Okay, but and okay, so the Fontaine-Mason conjecture then tells you, so I guess I only can give a rough overview of what I wanted to say. The Fontaine-Mason conjecture tells you that, or its proof, tells you that you can describe the Hecke eigensystems that occur in this cohomology of the system. Purely in terms of Galois representations. Okay, and the claim should be that using categorical local Langlands, one should be able to describe h1 at yq bar v lambda as the coherent cohomology. Or as cohomology of a coherent sheaf on a stack of Galois representations. Okay, and I guess for time reasons or time constraints, I won't be able to write down very precise formulas. Yes, sorry. Well, I mean, yeah. If I allow myself anyway not to write precise statements, then I have time. These are global Galois representations, but you want to use categorical local Langlands. Okay, and so if you look at this, this sounds very convincing, up to the fact that you can write out a formula, and in the EHES notes with Matt Emerton and Toby G, there is a written down formula. When I first discussed this kind of formula with Peter Schulze, he immediately complained about this, because this formula only uses information that you have with categorical local Langlands at the finite places, but not at the Archimedean place. And he said such a formula has to use categorical local Langlands at the Archimedean place as well. Which is true, but still the formula we wrote is correct. And I want to explain to you in this last 5 minutes, in some sense, why and what's happening here. The reason is that at P, we use p-adic local Langlands, and we consider this local system that's written up there in some sense in a way which is already present when one first started to talk about p-adic interpolation of Hecke eigensystems or of cohomologies. Okay, so the problem is such a formula should use local Langlands or categorical local Langlands over the wheels. Over the wheels, about which I know not too much. The further problem is that the space of global Galois representations has no map to the space of L parameters over the wheels. Okay, so spaces of Galois representations, Gal Q representations, don't map to kind of stacks or spaces of real L parameters. Okay, so yeah.
You're almost out of time.
Well, I mean, like, so this kind of
This is such a formula. The formula you mean this description?
This description of the cohomology, the description I haven't written down in terms of the cohomology of coherent sheaves on the stack of Galois representations.
Okay.
And well, because here I've wrote 2 reasons why this formula should not exist. In some sense, it's a good reason that I didn't write it down. So I will kind of now tell you how to overcome this, and how then one could write down a formula if I had more time. The stack of global Galois representations is, well, just think about the generic fiber of a deformation space of Galois representations. That's maybe the first best approximation for now. Just a continuous p-adic representations of the absolute Galois group of Q with prescribed ramification away from P. What? The coefficients are QP, or kind of Tate over QP, or whatever. Okay, so there's an obvious idea how to overcome this, that the Galois representations don't map to the space of L parameters over the wheels. Namely, if you restrict to the locus where representations are de Rham, okay, which is kind of anyway the only thing that you should see when you deal with something motivic like these local systems that we have up there. So this can be overcome. On the de Rham locus. Okay, but it's but the way how you overcome this is not that you only consider the Galois representation that you see at the wheels, but in some sense you only have to, you also have to use information from the de Rham locus in order to map to the space of L parameters. And this information, because here you have additional information at P at your disposal. Okay, so. Yes, in the end, yes, right. Well, up to that you might have extension or something like this, but this kind of scheme theoretically, it's not very nice, okay? So, but you see that here you have additional information at P that allows you to map to a space of real L parameters, okay? And this corresponds to something that you can do just on the automorphic side. You can, so instead of considering the local system VL as I defined it above, what you can do is you can move the information to P. So move this to the p-adic place. And this is how you actually, well, ever since in some sense, try to define what p-adic modular symbols are. Yes, right. But in some sense, I wanted to stress that this very classical procedure is the precise counterpart of a problem that you have with these kind of maps of spaces of L parameters. Okay, so I wanted to write down the formulas. So where's my formula? So I take I have the following isomorphism: H times V lambda times G of QP. And let me forget about the places away from QP. isomorphic to H times V lambda times G of QP, and it's a very innocent map. You just take X, comma V, comma G, or G at P, and you map it to X, comma GP inverse V, comma GP. Okay, so this exchanges a left and right action of actions of G of QP respectively KP, which on the left-hand side G of QP acts naturally on V lambda and KP, of course, trivially. And on the right-hand side, it's the other way around. Okay, so that's the kind of very classical down-to-earth way how you move the weight to P. And starting from this, you can now, instead of just taking these algebraic representations, you can move these algebraic representations in families. For example, you can embed into induced representations from a character, and then you can move these characters, and you have all this business of p-adic interpolation. Okay? And I'm out of time, and I should stop here by saying that this is in some sense, these things, these two reasons that cancel each other off, are the reasons that you can write down a formula for this category, for this cohomology, not using categorical local Langlands over the wheels, but instead using p-adic categorical Langlands, not smooth, but kind of p-adic locally analytic or something like this. Because this representation, V lambda as a representation of KP, certainly is not smooth anymore, but only locally algebraic or locally analytic. Okay, and I should stop here. Sorry for going a bit over time.
Are there any questions?
So you said things are uniquely determined for smooth representations, but what about all extra representations? Because it's just parabolic induction, so it seems you take.
Well, for all extra representations, the thing is
uniquely determined.
It's certain. Like I prescribe what it's supposed to be on induced representations, and I prescribe what this action of like tensor with an algebraic representation is supposed to be. Yeah, and then these two combined.
Subquotient of inductions of locally algebraic, basically. So you should.
What I mean, like,
what it is.
I think these two combined would tell you as well what you should have on all extra representations. Because like this allows you to this action of Harris-Chandler bimodules allows you to move from a Wermer to a dual Wermer or something like this.
Any very quick question before we head to lunch? If not, let's thank Eugen again.